Welcome to 2026. Right now, we are living through one of the most incredible moments in the history of technology. We've got this AI-fueled gold rush that's demanding silicon at a pace we've never seen before. But it's colliding head-on with a brand new reality. The global semiconductor world is fracturing. So let's dive in and break down what this really means for the future of tech. So here's our roadmap. We'll start with the new reality for 2026 and the geopolitical battlefield that's causing it. Then we'll get into the high-stakes foundry wars, look at the bottlenecks and breakthroughs that are shaping everything, explore the incredible role AI is playing, and finally wrap it all up with a clear strategic outlook for you. All right, let's be perfectly clear about the main idea right from the get-go. That old vision of a smooth, single, global supply chain for chips, that's a relic of the past. It's over. We're now in an age of strategic decoupling and national interests. This isn't some temporary blip. This is the new permanent landscape. And, the stakes here could not be higher. This market is just massive, and it's growing at a blistering pace, on track to more than double by the end of the decade. So when a trillion-dollar industry starts to break apart, the shockwaves are felt everywhere, from national security all the way down to the price of your next phone. That's why understanding this is so critical. So, how did we even get here? Well, this isn't just about market forces or business as usual anymore. We've entered a totally new phase, where geopolitics and national policy are the real drivers reshaping the world's most critical industry. Now, what's so fascinating about this slide is how clearly it shows the core problem. I mean, just look at that immense concentration of advanced chipmaking in just two places, Taiwan and South Korea. For leaders in the US, Japan, and Europe, this chart isn't just data. It's a flashing red light for national security. And it is fueling a multi-hundred-billion-dollar race to bring chip production back home. And of course, this has everyone scrambling to respond. In the US, you've got the CHIPS Act, designed to bring the most advanced manufacturing onshore. China is pouring money into its Big Fund 3, which is a massive state-backed push for total self-sufficiency, especially in the tools needed to make chips. And then there's Japan, going all in on its national champion, Rapidus, with the incredibly ambitious goal of mass-producing 2-nanometer chips by 2027. Every major power is placing its bets. And look, this isn't some theoretical policy debate. It's happening right now. Supply chains are literally being used as weapons. We've already seen China put restrictions on exporting critical raw materials like gallium and germanium, which directly hits global production. This is the reality of 2026. Access to technology and materials is no longer guaranteed. It's a strategic asset to be controlled. So all this geopolitical drama, it sets the stage for an absolutely epic corporate battle. The foundry wars have heated up into a furious three-way race for dominance between the reigning champ, TSMC, and its two very powerful challengers, Intel and Samsung. And each challenger is facing a totally different fight. Intel is in the middle of a massive restructuring, basically betting the entire company on a huge technological leap with its 18A process. It's a classic high-risk, high-reward gamble. Samsung, on the other hand, is fighting a battle for credibility. They've got the tech, but they've been plagued by manufacturing yield issues, which basically means the percentage of good, working chips they get from each silicon wafer is just too low. They have to prove they can deliver consistently to win back the trust of those big-money customers. Right at the heart of this whole thing is the race to perfect 2-nanometer chips. All three are moving to a new transistor design called Gate-All-Around, or GAA, but they're taking different paths. TSMC is taking a safer, more evolutionary step. Samsung is focused on reliability and cost. But Intel? Intel is making a massive leap, not just with its version of GAA, but by introducing a radical innovation called backside power delivery. This means flipping the chip's design to feed power from underneath, which is a fundamental shift that could give them a huge advantage. If it works, it is a true game changer. So how's Intel actually doing? Well, it's a really mixed picture. They've landed Microsoft as a huge anchor customer for their 18A process, and their Arizona fab is ready to go. But this has come at a brutal cost, with tens of thousands of layoffs. And this is a huge but. Reports are suggesting those initial 18A yields are still far too low for profitable mass production. That is a massive hurdle for them this year. Samsung is on a similar roller coaster. They scored a massive win by landing Tesla's next-gen AI chip business, which is a huge vote of confidence.
And yet, their big new fab in Texas has been delayed into this year because they're struggling to find enough customers. They're going after giants like NVIDIA, but whispers of 2-nanometer yields hovering around 50 to 60%, well, that's going to make any potential client really nervous. For Samsung, it all comes down to this. They have to fix their manufacturing consistency. But this race isn't just about who's got the best corporate strategy. The entire industry is pushing right up against the fundamental limits of physics. And solving these challenges is where the next era of computing is going to be defined, not in a boardroom, but deep inside the clean rooms and the research labs.
The AI boom is so massive that it's creating some severe bottlenecks across the entire supply chain. High bandwidth memory, or HBM, that's sold out well into this year. The advanced packaging needed to assemble AI chips totally booked solid through 2027. The actual machines you need to build new fabs have lead times of up to 2 years. And on top of all that, we just don't have enough skilled people to run all these new facilities.
So what's going to get us past these limits? First up is something called High-NA EUV lithography. Think of it as the most advanced printing press in human history, using extreme ultraviolet light to etch impossibly tiny circuits. Intel's the first in line betting on this for its future chips. The catch? Each one of these machines costs over 350 million euros. Yeah, you heard that right. Next is a breakthrough in packaging called hybrid bonding. Instead of connecting stacked chips with little bumps of solder, this technique bonds them directly, copper to copper. And it shows you the path forward. If you can't shrink sideways anymore, you have to stack smarter. This tech is absolutely essential for building the next generations of high-bandwidth memory. And if we look even further down the road, we see the next evolution of the transistor itself. Complementary FETs, or CFETs. The idea is simple but revolutionary. Instead of placing the two types of transistors next to each other on the silicon, you stack them vertically. This is a true 3D transistor, and it could be the key to keeping Moore's Law alive through the end of this decade. Okay, now let's talk about the force that's driving all of this: artificial intelligence. AI has this really cool dual role in the semiconductor industry. It's not just the biggest source of demand by far, it's also becoming the most critical tool for actually designing and building the next generation of chips. It's this powerful, self-reinforcing flywheel. I mean, just look at this breakdown of TSMC's revenue. High-performance computing and AI now account for 57% of sales for the world's most advanced chipmaker. That's more than double the entire smartphone market. This one chart shows you just how completely the AI gold rush is reshaping everything. But here's the other side of that flywheel. All of this incredible complexity is now being managed by AI itself. Fabs generate insane amounts of data every single day. AI models sift through all of it to find microscopic defects, which directly improves those critical yield numbers we talked about. It can predict when a 350 million euro machine is about to fail, and it even acts as a co-pilot for engineers, helping them design the next impossibly complex chip faster than ever. So, the crucial point is this: AI is both the destination and the vehicle. It's the gold that everyone is rushing to find, but it's also the new set of tools, the pickaxe and the shovel, that makes the whole thing possible in the first place. Okay, we've covered a ton of ground. The geopolitics, the corporate fights, the deep tech. So what does this all mean for you? Let's boil this all down into an actionable, strategic outlook for 2026. Here are the 4 key takeaways for 2026. First, the risk. This split in the global supply chain, it's permanent. You have to diversify, now. Second, the opportunity. The AI supercycle is very real, but it's physically constrained. Secure your HBM and advanced packaging supply immediately. Third, the wild card. Keep your eyes on Intel's 18A process. If they succeed, it's a 3-horse race. If they fail, TSMC's dominance just gets stronger. And finally, the threat. China's relentless push for self-sufficiency is going to create unpredictable, state-backed competition across the board. And this all leads us to one final critical question. For 50 years, Moore's Law was a global project, this predictable rhythm of innovation the entire world built upon. But now, in this new fractured landscape of national champions and strategic competition, who gets to own its future?